Hello everyone, my name is Bashir Al-Kadir. Welcome to this session, welcome to this talk. Today I want to talk to you about learning dynamical systems with side information. So let me tell you what that's all about. Consider a continuous time autonomous dynamical system given by the equation x dot equals f of x. F here is a function from Rn to Rn and is called a vector field. In dimension 2, or when n equals 2, I can represent this vector field as a string plot. The setting I'm interested in is one where f is unknown to me, meaning that I don't see these arrows in the background, and my goal is to learn f on some compact set omega of interest from a bunch of trajectories. More specifically, what I have access to is some measurements of the state variables and their time derivatives, and I'm going to assume that these measurements are scarce and noisy. So I need to exploit what I call side information. And by side information, I mean any information you might have about this dynamical system on top of the trajectory data. It could come from common sense, some domain-specific knowledge, laws of physics, etc. And whenever I bring up side information, I'm going to call on the side information guy, and his job is to give me the side information that I need one by one. Side information could be, for example, the knowledge that my system has an equilibrium point somewhere. It could be that I know of some set that is invariant with respect to my dynamical system, meaning that trajectories that start inside this set stay inside this set forever. It could be the knowledge of two sets A and B, such that trajectories that start from A always reach B or never reach B. It could be that I know the sign of the time derivatives of the state variables on some regions of the space, or it could be that I know that some components of my vector field are monotone on some regions of the space. So our approach is to fit a vector field to our data by solving a least squares problem. And I'm going to parameterize the candidate vector field as a polynomial, meaning that the entries of my candidate vector field are polynomial functions of the state variables of some degree, let's say 4. And the coefficients of these polynomials are the decision variables of my least squares problem. So what I'm going to show you is how to impose the side information that I know the true and unknown vector field satisfies. How can I impose those side information on my candidate vector field? And I'm going to show you how to use SOS or sum of squares techniques to impose that side information in practice. And I'm going to be very concrete in this talk. I'm going to take two numerical examples to showcase this technique. The first one is from epidemiology, and the second one is from mechanics. Okay, so let's see the first numerical example. This one is from epidemiology, as I said, and this dynamical system that I'm going to show you has appeared in the literature as a model for the spread of a sexually transmitted disease like gonorrhea in a heterosexual population. So here I have two state variables, x1 and x2. x1 represents the fraction of infected males, x2 represents the fraction of infected females, and the dynamics for the time evolution for the infection rate of males, for example, is given by the following equation. As you can see here, there are two terms. The first term is the recovery rate, so I'm assuming here an exponential rate of recovery. And the second one is the infection rate. And as you can see, it's proportional to 1 minus x1, which is the fraction of males which are not infected yet, times x2, which is the fraction of females that are already infected that could potentially infect the males. And of course, there is a similar equation for the spread of the disease in the female population as well. So in summary, what I have here is a vector field in dimension 2. So I can plot it for you. And for the following values of the constants ai and bi, the string plot of the vector field f looks like this. So now I'm going to assume that I don't know the value of these constants ai and bi. Actually, I'm going to assume that I don't even know that f has this special structure. So I don't get to observe these arrows in the background, so I don't know f. What I have access to is a single trajectory. More precisely, what I have access to is 20 noisy measurements from a single trajectory. And from it, I'm going to try to recover the vector field f. So if I fit a polynomial of degree, let's say 3, to this data by solving the least squares problem I showed you earlier, you get a vector field that looks like this. Now, if you look closely, you can see that this vector field is trying to do the right thing next to the observed trajectory, but its behavior otherwise is really bad. So what can we do to improve this? Well, we can use side information. So what kind of side information can we come up with here? Well, one thing we can say is that the origin should be an equilibrium point. And that's simply coming from the fact that if there is no male or female that is already infected, then the disease cannot spread. And as you can see here, this side information is already satisfied by the true vector field, but is not satisfied by the vector field we just learned. So what we can do is add this as an additional linear constraint to our least squares problem and solve it again. And if we do that, we get the following striplet. Okay, what other side information can we think of? Well, the side information guy is telling me that I should look at the unit box and it should be invariant. And when you think about it, this is simply coming from the fact that x1 and x2 represent fractions, and as such, they should be bounded at all times between 0 and 1. So how can you impose that a set is invariant with respect to the vector field during the learning phase? So for simplicity, take a set that is defined by a single polynomial inequality g of x greater than 0. I want trajectories that start inside the set to never leave it. So how can I impose that? Well, I have to look at the times where my trajectory meets the boundary of the set. In particular, at those points, g of x should be equal to 0. And at those points, I should look at two vectors. The first vector is the gradient of g, which is pointing at the direction of biggest increase of my function g. And the other direction I should look at is the direction that f is telling me to take. And for my trajectory to be invariant, I need the inner product between these two vectors to be non-negative, because otherwise I would go outside of the set. As you can see, what I need to impose now is that some quantity that depends linearly on my vector field should be non-negative on some regions of the space defined by polynomial equality or inequality g of x equals 0. And this is exactly the kind of constraints that sum of squares techniques can handle and transform this constraint into a valid semi-definite programming constraint. So when I do that, I get the following vector field. And as you can see now, the arrows are pointing inside or inwards of this of the unit box. Let's consider a last side information. So here, the side information guy is telling me monotonicity. And actually, for me to explain this to you, it will be easier for me to tell you why the learned vector field does not satisfy this side information. So let's say I fix the number of infected males to 40%. So I am on this vertical line that you see here. And now what I'm going to do, I'm going to track the rate of infection of males as I move up this vertical line. So if I'm here, there are almost no males infected in the population. And my vector field is telling me that I should expect about 5 males to be infected every day. Now, if I increase the number of infected females in the population, the vector field now is telling me that almost no males should be infected anymore. And this simply does not make sense. If there are more females that carry the disease in my population, I should expect the rate of infection for males to increase, not to decrease. So this is not satisfied by this vector field I just learned, and I need to impose this additional constraint explicitly. And it's not very hard to see that this constraint is a negativity constraint on the partial derivatives of the first component of my vector field. And there is, of course, a similar equation that I get by switching the roles of males and females in this explanation I just did. And these are exactly the kind of constraints that can be enforced by the sum of squares techniques and by semi-definite programming. So I do that, I'll add these constraints to my least squares problem, and I get the following vector field. And as you can see now, right now we're starting to capture the right qualitative behavior of the true and unknown vector field, even though we have learned it simply from 20 noisy measurements from a single trajectory. Let's now move on to a second example, this time from physics. This is the simple pendulum. And the dynamics is given by this second order differential equation. By a simple and classical trick, I can transform it to a first order differential equation, which leads to this two-dimensional dynamical system. So lucky for us, we're working in 2 dimensions here. So I can draw here for you a stream plot of this vector field. Let's imagine now that this vector field is unknown to me, and the only thing I have access to is trajectory data. So more specifically, I take my pendulum, put it in some initial condition, let it go, and I'm going to track this trajectory, and I'm going to make 5 noisy measurements. Then again, I'm going to take the pendulum to a different initial condition, I'm going to let go again, and I'm going to make 5 noisy measurements on this trajectory again. So overall, I have 10 noisy measurements, and that's all I have. So let's think about what side information we can use here to help us with the task of learning. One obvious side information is symmetry. If I flip the pendulum around the vertical axis, the dynamics does not change at all. What this means for the vector field is that if I rotate it by an angle pi, I get back the original vector field I started with. As it turns out, this is a simple linear constraint that I can simply add to my least squares problem. The second side information is that gravity always pulls you down. This is something you might know without knowing exactly the expression of the gravitational force. What this means is that when theta is positive, your speed, theta dot, should decrease because gravity is pulling you towards the origin. And when theta is negative, your speed should increase in absolute terms. Okay, the third side information is that the system is Hamiltonian, and this is simply coming from the fact that there is no dissipation of energy through friction with air, for example. So this was the list of side information that I'm going to use. Let me now show you the added benefit of using this side information during the learning phase. If I fit a polynomial vector field of degree 5 to my data by solving a least squares problem, I get this vector field here. Again, you can see that it kind of overfits to the noise in the trajectory data, right? And its behavior outside of the observed trajectories of the observed regions of the space is not correct. So let me now add the side information that I showed you one by one. So the arrows are going to move, and we're getting new solutions. And as you can see, the behavior of the learned vector field is getting better and better, even though we have learned it just from 10 noisy measurements. I'm going to end this talk by a theorem that justifies our choice for working with polynomial functions as candidate vector fields. You can think of this theorem as a density result, like the Stone-Weierstrass approximation theorem for vector fields, and there are constraints that come from the dynamical systems world. So keep in mind this is a simplified version of the theorem, and I invite you to take a look at our paper for the full statement, a more precise statement. So the statement is as follows. For any vector field f, there is continuously differentiable and defined on some compact set omega for any time horizon that you care about t, for any desired accuracy epsilon, if f satisfies any one of the following side information that I'm going to list now: equilibrium point, a symmetry condition, the negativity of some components of the vector field on some regions of the space, the negativity of the partial derivatives of the components of my vector field, invariance on some given set under some conditions, a gradient or Hamiltonian structure. Then there exists a polynomial vector field such that trajectories of f and p remain within epsilon distance of each other for all time t between 0 and capital T, and the polynomial p satisfies the same side information constraints that f is known to satisfy. So now you can ask, what if f does not satisfy just a single side information, but a combination of side information? Can I still get the same guarantees that there exists a polynomial, such a polynomial vector field P exists? Well, in general, we prove that polynomial vector fields might fail to satisfy some specific combinations of side information. But if we allow for some room of error delta, and we can take delta as small as we want as long as it's positive, then there is actually a polynomial vector field P that delta satisfies, not necessarily exactly satisfies, but delta satisfies any combination of side information you care about while staying close to the vector field F. And as a bonus, all such properties of the polynomial vector field P come with a sum of squares certificate, meaning that we can impose them during the learning phase by semidefinite programming. Thank you so much for watching. I hope you enjoyed the talk.